Hi everyone, my name is Nurul Amizdul Shafira, and today my partner Nurul Maisara and I are going to talk about work energy and power using calculus. In our daily life, we use energy all the time, whether we're moving things around or running machine. But in high school physics, we usually keep things simple and pretend that force and power stay constant. In real life engineering, that's rarely true. Forces change constantly as things move. When a force is steady, we just multiply force time distance. But when the force keeps changing, we have to use integration to add up all those tiny changes over the path. Now on slide 2, we can see how this leads to the work energy theorem. Kinetic energy is just the energy an object has when it's moving. If we take Newton's formula, F equal to ma, and swap the acceleration part using the chain rule, we can rewrite our work integrals in terms of velocity. When we solve this integral, we get the simple equation, which is the simple equation proves the work energy theorem, where the total work done on an object is equal to how much its kinetic energy changed. On slide 3, we bring time into the picture with power. Usually, average power is just work divided by time, but real machine push out different amounts of power from moment to moment. Instantaneous power is how fast work is being done at an exact second. We can write this as a basic differential equation. If we rearrange this and integrate both sides, we get the formula. This lets us figure out the exact work done or energy gain over any amount of time. Now I'll pass it over to Maisara to show you how we applied this to an actual engineering problem.
Thanks, Ami. To see how this works in real life, check out our test scenario on slide 4. We have three electric cargo lifter, Model X, Model Y, and Model Z. Each lifter has to lift a heavy 400 kilogram platform straight up from rest over a 4.0 second test. Each machine push out power differently over those 4 seconds. Model X equal to 800T. Model Y kicks in with a fast surge 300T square. Model Z grows exponentially equal to 500 exponent 0.5T. Our job was to integrate this power function, find the total work done, and see which machine got the platform moving the fastest. Let's look at the math for that 4-second window. For model X, the power ramps up linearly with 800T. Integrating 800T over 4 seconds gives us 400T squared, which evaluate to 6,400 joules or 6.40 kilojoules. Plugging 6,400 joules into our work energy formula give a final speed of 5.66 meter per second. For model Y, power surge quadratically with 300 t squared. Integrating 300 t squared give 100 t cubed, which over 4 seconds also comes out to 6,400 joules. Solving for speed gives the exact same result, 5.66 meter per second. Lastly, model Z grow exponentially with 500 exponent 0.5t. Integrating this give 1000 exponent 0.5t, which evaluate to 1000 exponent square minus 1000, giving roughly 6,389 joules or 6.39 kilojoules. Solving for speed give 5.65 meter per second. Moving to slide 5, this comparison gives us a super interesting result. Even though Model X and Model Y deliver power completely differently, they both transfer the exact same total energy, which is 6.40 kilojoules over the 4 seconds. Because they transfer the exact same energy, they tied for first place with a speed of 5.66 meter per second. Model Z actually start off stronger with 500 work right at the beginning, while X and Y start at 0. But over this short 4-second window, its total energy output ends up slightly lower at 6.39 kilojoules. So it finished just a tiny bit slower at 5.65 meter per second. Finally, on slide 6, why does any of this matter in the real world? First one, electric car. Car control units use this exact curve. A smooth, steady ramp like Model X is great for everyday driving, so passenger don't feel jerked around, while a search profile like Model Y is used in sport modes when you want quick power. Second one, industrial warehouses. Knowing these power numbers help factories plan their electricity use so they don't blow fuses when heavy cranes start up at the same time. Lastly, robotics. Robot arms use this calculation so they can move delicate parts smoothly without shaking or breaking them. That wraps up our presentation. Thank you for listening.